Now let's start a new chapter, the system response or um, response of measurement system. Okay, so from system point of view, if I have input to a system, and I have output. Okay, so in this case we have measurement systems. So we want to know how does the measurement system respond to the input, which is our output. So from system point of view, input output relationship, or you have the excitations, you have a response, or you have input as a measure end, output as a readout output of the measurement systems. Yes. So we want to know how does the measurement system respond to your input or the measure end. Okay, so let's start with basics. What would be the ideal case? In other words, let's put it in the math. What is this? So of course in time domain, that will be the differential equations relating output to the input, or governing equation. Or in frequency domain, that's differential equation. Or in frequency domain, we said it's transfer function. So the question is, what will be the relationship between input and output for ideal measurement systems? What do you want to be? Of course, it should be what you read is what you measured. In other words, we want these to be a 1, input equal to output, or literally we can say it's a constant K, output input relationship. In terms of transfer function, that's 1, or K, that's ideal case. Okay, it works both. There's no time delay, just a pure amplifications. But that's an ideal case. So if you look at this, in frequency, it should be constant, which is good. However, that's not a situation. Even this for this model, a constant transfer function is a constant. Again, like a potentiometer, you do have a constant, but it's assuming there's no frictions or no damping effect. So in reality, if we from mechanical point of view, you always have MCK effect. You have mass in terms of inertial, C in terms of damping, K in terms of stiffness. So for example, when we say for spring, we for ideal spring or linear spring, force is proportional to deflection K, X. But when we do this, we are assuming that there's no inertia. So it's massless spring, no inertia, or there's no damping in the spring. In reality, more or less, there are always these effects, one or the others. Okay, so ideal case is a constant, but in reality, you always have inertial effect, then effect. So that's why we talk about is time dependent. You will have either max inertial, damping, stiffness effect. So we'll start with a more realistic case and talk about the first order system or second order system. And a lot of physical systems, they are even higher order. But if you remember in 340 or 34, in ME340 or the new sequence ME3401, we'll only talk about first and second order system. And why is that? Well, it's not because it's too complicated, so we don't want to deal with. But both in time and frequency domain, we can always break the higher order system into a bunch of first order samples. A bunch of first and second order system. That's why as long as we understand the characteristic of first and second order in time domain and frequency domain, and then we can find the response or find the characteristic of higher order easily. Okay, so we'll start with the first order system. system model meaning mathematical model, and like we said, when we relate the relationship, let's use same thing, block diagram, input as y, output as x. Okay, so lowercase will represent time domain. So relating these output to the input in time domain, that's differential equations. In Laplace domain, that's transfer functions, which is capital S, Y, S. Okay, so first order meaning the highest derivative of the output variable is 1. So differential equation, we have, let's put a standard one, tau s dot plus x equal to k, capital K, times y. So any kind of system, mechanical, electrical, fluid, thermal, if you can represent in terms of this form, then the solution will be easy to be obtained once we get to know, or once we get we are able to characterize this kind of systems. Okay, so first order systems, this is the standard one, and we call K is steady state. Again, or in measurement system we call static sensitivity. Okay, tau is referred or is defined as the time constant unit-wise is always in second. The unit for K is output unit over input unit. So let's one more time, let's specify y is our input variable, input, x is output. Okay, so because this is the first derivative, that's what we call is a first order system model. First order system model right here. Okay, now let's find out what's the system response. Okay, and why is it important to find K and tau to represent these systems? Okay, and we will start with response. So let's say let's say step response, if y of t is a constant, or let's say step input a u t, that's defined in graph t. In other words, nothing happened before the time start. After the time start, the values of y of t jump to an amplitude of a y of t. Okay, so this is step input, and U of t is unit step input, A is amplitude, unit step input meaning the amplitude is 1. Put now what's the output? So if you remembered when we define input output, the output will be the output due to the output of step input. That's what we normally call this step response step. And mathematically, that's our S of t, which is you know the differential equation, which is tau s dot plus x equal to k y of t. You know y of t, and if you know initial conditions, and mathematically we want to find what is S of t, what's the solution of S of t. Okay, so this one should be already discussed in your 3401. So since this is standard input, standard solution, so simply just give you the final solutions, and on the breadboard I will also give you the table or the formula for this one. You will be able to see it right here. Step response of the first order system. First order system is defined as tau s dot plus x plus k times y of t. So the step response x of t will be in this form right here. Okay, so we'll just copy down. S of t equal to s dot not e times k times a 1 minus e t over tau. Okay, and of course in terms of response, we can say this part right here is due to the initial condition. That's what we call free response. This part right here is due to A is input amplitude of the step function. So this part right here is related to the input we call force. Force response. Okay, or look at from the other point of view, you can rearrange these equations. You can get what x minus ka plus k times a. Okay, so this part right here, let's put it one more time, S of t. This part right here, we can also from time dependent signal right here. When time goes to infinity, this term goes away because exponentials. So we call this transient response. This one is steady state. Steady state response. Okay. Now let's take a close look. Particularly, we want to know input output, the force response. So if we look at this force response, which is Ka, this is tau. Now let's plot this one in terms of time. Tau is positive. Okay. In other words, what happens when time goes to infinity? This is in time, that's t. In second, s of t. When time goes to infinity, this term goes away. This is k times a. So it's from 0 slowly exponentially increase to a steady state value. Okay. So remember we say K is steady state gain. So what does that mean for a second order system? Meaning at the steady state conditions, K is simply amplify the input, the value to amplify the input. So that's why we said K is defined as steady state gain. Okay, and in a sense it determines how much the system amplified the input, the measurement system or the system amplified for K. Now how about for T, tau? Let's see what happens when T equal to tau. Let me put it here. Let's put T equal to tau. Let's put this one back to the equation right here. So S of t tau equal to K times A times 1 minus e raised to tau over tau. Ka e minus 1, which approximately you will get 0.632 K times A. In other words, time constant is the time required for the output reach 63.2% of the final values. At this point, tau 0.632 K times A, 633. So why is it important? Because this one tells the system, tells us how fast the system responds. The system responds to the input. If you have smaller tau, meaning it takes shorter time to reach steady state. So in terms of a sensor design, you actually need to have a smaller time constant, so it will have faster. Or from the other point of view, it takes less time to reach steady state. Okay, so what is tau? Tau determined how fast the system respond to the excitations. Okay, so let's say if I have two systems, they happen to have the same steady state gain. If I have a system first order and I have the second one, the red one, so this is system 2, this is system 1. Which system has faster response? Of course, you would say the answer would be system 1. Okay, so how do we justify? You can see it takes longer time for system 2 to reach steady state, but a lot of time we actually use the time constant. 63, please. Time constant. Tau 2, and this is tau 1. So, of course, tau 2 is greater than tau 1. The smaller time constant, the faster response.